Hi engineers, in this section we are going to discuss about the classification of magnetic material. So when come to the solid, they are mainly classified into two types magnetic material. One type of materials has atoms having a no permanent dipole. So this is the classification based on whatever we discussed now, that is magnetic dipole moment based. So atoms having no permanent dipole moment, those are come under diamagnetic material. And when come to other section, atoms having permanent dipole moment, these are paramagnetic material, ferromagnetic material, antiferromagnetic material, and ferrimagnetic material. So this is the classification. Now we will move further and classify these magnetic material. Basically what we told, one type of material, diamagnetic materials, there is no magnetic dipole moment generally present there, right? For other dipole moments exist, and based on the orientation of the spins of the dipoles, paramagnetic orientation will be this, and ferromagnetic all are oriented in the same direction. In antiferromagnetic, they are phased, some are upwards, some are downwards, means opposite direction oriented. Then ferrimagnetic material, there is if we carefully observe, there is a difference. The dipole, some are small, some are large, maybe one side large, another side small. Orientation is opposite tone, but when come to ferromagnetic, they are same direction. So yeah, before going to further, we will broadly classify as diamagnetic, paramagnetic, ferro, antiferro, ferrimagnetic material. Now we will see one by one. So when diamagnetic materials which become weakly magnetized in the direction opposite to the applied field. So generally, if no field is applied, there is no magnetism, because these are the diamagnetic materials. And generally diamagnetic materials, all electrons are paired, right? All electrons are paired. In those materials, diamagnetism exists. So in the universe, every material is a diamagnet, but due to special properties, other para, ferro, antiferro properties will dominate. So as a default, all materials are diamagnetic materials. And when come to this magnetic movement, generally they won't exist, or if we apply magnetic field, they may be slowly arise, weakly magnetized, and that too, whenever we apply the magnetic field, these magnetic moments aligned opposite to the direction. That type of materials what we call diamagnetic material. So when come to diamagnetic material, the properties are very straightforward. Its relative permeability is less than 1, and magnetic susceptibility is negative, and psi is independent of temperature and magnetic field strength. Net magnetic moment is 0. That's why there is no magnet, and no permanent dipole. No permanent dipoles exist in diamagnetic material, and diamagnetic materials repel magnetic lines of force. So whenever we keep a diamagnetism in a magnetic field, it repel the line, like magnetic lines are there. If it is magnet, then we will see. And most our superconductors are diamagnetic, that's why they will show the Meissner effect. And examples are organic materials, bismuth, zinc, copper, silver, gold, etc. So all these materials are diamagnetic material. Next comes the paramagnetic materials which become weakly magnetized in the direction of applied magnetic field. So without application of the field, the dipoles exist, but they are randomly oriented. Magnetic moments different directions. So whenever we apply the magnetic field, they oriented in the direction of applied field, along the direction of applied. Those materials are called paramagnetic material. Now when come to the properties, its relative permeability is greater than 1 but very small, and magnetic susceptibility is a low and positive. When come to dia, it's a negative. Then psi is independent of applied magnetic field H, but depends on T. That gives Curie-Weiss law. Psi is equal to C by T minus theta. Then net magnetic moment, mu m, not equal to 0. So mu m is not equal to 0. Permanent dipoles are present. In diamagnet, no permanent dipoles, but here permanent dipoles exist. Paramagnetic materials weakly attract the magnetic lines of the force. So whenever we keep the paramagnetic materials in magnetic field, they weakly attract the magnetic line. Spin alignment is random. Example for this: sodium, aluminium, manganese, phosphorus, etc. Then ferromagnetic materials. So materials acquires high magnetization in a weak magnetic field also. The main reason for this is they have the oriented dipole. And when come to the properties of ferromagnetic materials, relative permeability is very high compared to 1. Magnetic susceptibility is large and positive. Magnetic susceptibility, net magnetic moment, mu m not equal to 0. These magnetic materials possess permanent dipoles are present, so they will possess permanent dipole. Ferromagnetic materials attract the magnetic lines of force strong. So when come to paramagnetic, they weakly attract. When come to dia, they will repel. Spin alignment is parallel and is in the same direction. These materials exhibit hysteresis. These materials consist of domains. So based on the Weiss domain theory, we will explain these ferromagnetic properties. Example: ferrous, cobalt, nickel, gadolinium, etc. Then comes antiferromagnetic material, materials in which spin alignment is anti-parallel and net magnetic moment is, so spins of neighboring atoms are aligned anti-parallel. So these spins are anti-parallel. Magnetic susceptibility is a small and positive. Magnetic susceptibility greatly depends on the temperature, right, as shown in the diagram. Then net magnetic moment equal to 0. So this net magnetic moment is 0, and the Néel temperature we can see. Below the Néel temperature, this magnetic susceptibility is slowly increasing. Néel temperature, it's maximum. As I go on temperature, its psi value go on decreasing and finally became 0. Then these are Fe2O3, manganese oxide, chromium oxide. These type of the material shows antiferromagnetic nature. And ferrimagnetic materials, materials in which anti-parallel spins of different magnitudes and large magnetization arises. So ferrimagnetic material, material in which anti-parallel spins of different magnitudes and large magnetization arises. Here this one, opposite spins but different anti-parallel spins. Spins of neighboring atoms are aligned anti-parallel of different magnitude. Magnitudes are different. Magnetic susceptibility is very large and positive, right? This is ferri. Other side it is para. Magnetic susceptibility greatly depends on the temperature. Net magnetic moment not equal to 0. Above Curie temperature, material behaves as paramagnetic, while below the temperature it behaves as a ferrimagnetic material. This is the critical temperature. Examples of ferrous, ferrite, nickel, ferrite, etc. Then these are the overall idea how the temperatures versus magnetic susceptibility graphs will be, and the alignments of the spins as well. Now comes in exam, sometimes they will ask to compare the types of magnetic materials. In that scenarios, we have to make a table like diamagnetic material, para, ferro, antiferro, and ferrimagnetic material. Then we have to compare each step. Net magnetic moment exists in the presence of magnetic field in opposite direction. Net magnetic moment exists in the direction of applied field. In the direction of applied magnetic field, this is opposite direction. Large net magnetic moment exists in the direction of applied field, in the same direction, and in the direction exists in the direction. So when come to diamagnetic, it's opposite the direction, remaining all in the same direction. But ferromagnetic material, it's a large net magnetic moment. There is an induced magnetism opposite to the applied field. There is an induced magnetism in the direction of applied. So in the direction, once the first point is in the direction, second one is also on the same line. Third one, it repels the magnetic lines of force due to external magnetic field. So diamagnetic repels, it allows pass through it. It allows large number. It limited number it will allow, but when come to ferro, it large number. It allows magnetic lines of force to pass through it. It allows large number of lines of force pass through it. Next set, relative permeability. It's a negative value less than 1, and it's a greater than 1, much greater than 1, greater than 1, much greater than 1. Then since the induced magnetic moment is opposite to the direction of the applied field, the intensity of magnetization is negative. M is negative. Here M is positive and moderate. Then here M is positive and high. M is positive and moderate. M is positive and high. Right. So whenever you are writing, you take care of the key points, you can write the remaining thing. Susceptibility is negative, low and positive, high and positive, low and positive, It's a high and positive. Then susceptibility and temperature relation. It's a plays the key role. It's a susceptibility size independent of the temperature. In all other cases, it's depend, and the relation is this is the Curie's law, this is Curie-Weiss law. This is also same relations it will. When come to examples, alkaline metals and transition metals, it's a transition and rare earth metals, salts of transition elements and ferrite. So these are the different combinations, right? Okay, thank you.